Okay, so let's start today's lecture. So today is the second lecture on classification. So today we'll talk about some regression approaches to classification. Okay, so classification. Last time what we did was we did some probabilistic modeling where we assumed that each class had a certain distribution, for example, a multivariate normal distribution, and then we saw that in some cases we got a linear classifier, a linear decision surface, and in some other cases we got a quadratic decision surface. So today, let's kind of think back a little bit back to regression and see if, what would be regression approaches to classification. And later on, as we'll see, what I'm going to talk about today actually ends up being used partially in current deep learning architectures. So again, our problem is you have xi, yi. This is the training data. You have xi belongs to rd. You have now yi, remember, we are doing classification. Let's consider the k-class classification problem. So that means instead of, last time we considered k equal to 2, class 1 and class 2. But today, let's be a little bit more general in the beginning, right? Where we consider a general k-class classification problem. And of course, when k equal to 2, then you will get the 2-class classification problem. So we're going to actually say that our yi belongs to rk. And this is going to be the k-class classification problem. Okay. And then, of course, we have I equals 1 to n, capital N being the size of the training data. So just as we had before, remember just writing it out. I have my training points. Let's suppose I have x, first component, second component, and there are d components. Okay. And similarly, we have y, which is now k. Okay, so remember that this size is d. It's d-dimensional. And this is k-dimensional. And what we will say is that y is an indicator vector, right? Which basically means that it has just one, okay, in the jth position, okay? And that basically, so suppose this is yi, and this means that it is a way of encoding that xi belongs to class J. Okay, so you can think of it as the jth position. You can also think of this as the jth column or row of the identity matrix. So that's how we are kind of encoding the classification problem. And then what we want to do is, just as we did before, a linear method for regression, and let's look at a linear method for classification. Okay, so my coefficients are going to be w's. So w0 plus w1 x1 plus w2 x2, and I have d plus 1 coefficients, w d x d. Okay, so this is a linear fit. And I can think of, I'll denote this as y given x. Okay, y of function of x. And generally, these kinds of, in the classification setting, these kinds of y's are called linear discriminants, because what they are trying to do is discriminate between from one class to the other. So each class will actually have a different linear discriminator. Sorry, discriminates. This should be discriminant. Okay, so I'll have wj. This is a vector. Okay, transpose X plus Wj naught. Okay, and this is a linear discriminant for the jth class. Okay, so let's write it out again. Suppose I take all the, I'm given a training data set. I'll have training examples for class C1, training data points that belong to class C2, and so on. So let's, for the moment, in the training data set, list all the X's that belong to class 1, then class 2, then class 3, and so on, right? So I'm going to arrange my training data in this matrix, right? Just very similar to what we had done for the linear regression problem. And now I have X1, X11, X12, X1D. So I basically listed the first training data point as the row of this matrix. And I'm going to do the corresponding linear discriminant, right? And that is going to be W10, W, and then this part over here. Just if I want to keep this notation, I'll just say that this is W1 bar. Okay, this is of size D, and this is of size D, and this is, of course, 1. Okay, and there's going to be N, and I'm going to arrange all the training data for C1 over here. Okay, so what that means is that when I take this and I multiply with the corresponding linear discriminant, okay, I'll have other linear discriminants, W20, W2 bar, and so on. So I have K classes, so I have K linear discriminants, K0, WK, okay? And what I want to happen is that the first, when I take this times the first linear discriminant, I want to get 1. But for all the other discriminants, right, I will get zeros. These are K. This is K. This is K. So that means that, X, this is, in this language, W1 transpose X plus W1 naught. I want that to give a 1. But for the other discriminants, I want this to give a 0. So this now becomes the corresponding yi, which is like this one over here. Okay. Similarly, the second data point belongs to 1, and my first few points belong to class C1. So I have this pattern, and if this belongs to C2, what I will have is 0, 1, 0, 0, 0, 1, 0, 0, and so on. And then when I have class CK over here, right? So class CK, there'll be some last point, which is xn1, xn2, xnd. Okay, and in between there'll be something which is 1, xy, xi1, xi2 through xid. Okay, and this will be 0, 0, and a 1 in the kth place. Okay. So what I want is that this is approximately equal to this. Again, we don't want to overfit, but we want to want to fit to the training data. Let me call this matrix as X. This is the matrix of training data, very similar or almost identical to what we did in linear regression. This now is the matrix of coefficients. And you'll see that basically there is a vector for every class, which is the linear discriminant. Okay, so this is x times w, and this matrix I can call as y. Okay, so what I want to find coefficients w so that it gives me xw is nearly equal to y. Okay, now we've seen this before, and you might say, okay, I've also said in the beginning that, I'm doing kind of a regression approach. And then you might ask, oh, what do I mean by xw is nearly equal to y? Right, so one can potentially, I'm not saying this is actually going to work well, but one could potentially do the following, right? Is to think about trying to find w such that this is minimized, which is the square error. And if you think about it, if you remember, the solution to this is x transpose x times w star. I'm skipping all the steps in between about taking the gradient and so on, is equal to x transpose y. So note that the difference from linear regression was that in linear regression, when we looked at only one target, right, we only had one single column of y's and one single column for w's. But here, what we are saying is we have k classes, so we'll actually have k different columns of y, and similarly, we'll have one coefficient for each class. Okay. And then if w x transpose x is invertible, then I will get this solution. So that could be like a first regression approach that you might use for classification. Okay, and remember that x w star will be the prediction on the training data. Okay, so now just think about it. I want a new x, little x times w star would be the prediction. What will it give me? It'll give me a k-dimensional vector, right? K-dimensional vector. Remember that w is d by k. Okay, w belongs to r d by k. So when I take x transpose,
D or
which
D
is,
plus one, sorry.
sorry, go ahead.
Is it D or D plus one? Okay.
Yes, good point. I did include d, right? So there's one over here. So good point. Thank you. This is d plus 1 by k. Okay, and remember that x is r. So remember, I'm doing rd plus 1 because it's of this form. Okay. So d features, but the first one corresponds to the bias term. I think that looks like a 1, so. Okay. And what you would like is, you would actually like this x transpose w star, like there are k numbers. You want it to be 1 if it belongs to the class. So suppose this belongs to, this is something which is close to something on the training data, and it says that this is 0.98, right? Maybe you want these to be kind of probabilities, right? Maybe this is 0.01, this is 0.02, and so on. That's what you would like, right? And this would be the jth position if xi belongs to Cj, okay? However, the above, right? And when I say the above, I am talking about this because this is given by a least squares problem. In the least squares problem, really, right, when I do xw star, there is no guarantee that these values will actually be probabilities or so on, right? In fact, they can actually be negative, right? So this, the above w star, can lead to x transpose w star being of the form, some negative number over here, some positive numbers here, nothing related to probabilities. Okay, and clearly, this is not a good approximation to an indicator vector. Okay, which is kind of this form, 0, 0, 0, 1, 0, 0. Okay, often this is also called a one-hot vector. Okay, so just least squares, for classification has obvious drawbacks. Okay, it is kind of like an obvious method to try, but when you look at it, you realize that the values that you get really can't be interpreted as probabilities, so it's really not a great method. Okay, but we are just introducing it, and later on you will see that actually when we come to deep learning, then you can actually have different nonlinear functions that can take these real numbers and then map them onto, let's say, a probability distribution. There's something called softmax, which does exactly that. It'll basically take a vector and it'll map into numbers between 0 and 1 that can be interpreted as probabilities, and the sum of those numbers will add up to 1. So we'll come to that, okay? But classically, the above that I've done is, something to look at, but then also quickly disregard and say, okay, this is not really a very good method. But I just wanted to kind of introduce that because, it's an obvious thing to try. Any question? So we've so far actually introduced two methods, right? One through probabilistic modeling and one over here. And actually, neither is that great a method. Okay, it's not really what was used in practice even before the days of deep learning. So let me now talk about one very, very popular method, which before the days of deep learning, everybody used to do. This logistic regression I'll talk about, and then also I'll talk about support vector machines. So these were the most popular methods of doing classification. So logistic regression. And it's actually very good to understand this, even with the current, deep learning methodologies. Okay, so let's do a little review. Okay, last time when we did probabilistic modeling, right, what had we done? We had modeled each class as a Gaussian with covariance sigma. Okay, and if I'm not going to derive it and so on, but the rule that we had got was something like this, that we were interested in the posterior, which is P of Ci given X. Suppose this is the K class problem. And I was trying to distinguish it from a two-class problem from the Ci and Cj. Then this log of the posterior was the log of the prior probabilities, the ratio, okay? And then there was this linear term, or so remember, this is I'm assuming that the covariance is identical. So the quadratic term goes away and you get mi plus mj. You can look back at the notes from last time, and this was what we got. Mi minus mj plus x transpose sigma inverse m1 minus m2. So this is the linear term, right? So this part you can think of as, W naught. And then this is the linear term, and I can think of it as W1 W transpose X.
So the last parenthesis is also mi minus mj, right? Not
Thank you for keeping me honest. And it is mi minus mj. Okay. So you see from here that, even though we did this probabilistic modeling, we finally got a decision rule of this form. The problem with, like I told you last time, is when we try to model each class as a Gaussian with covariance sigma, is that first you have to actually try to estimate sigma for each class. And that actually becomes complicated because sigma has, a number of parameters that is quadratic in the dimensionality, right? So while this approach, allows you to get to W naught without really doing much computation, right? I mean, you have to do sigma inverse, but once you estimate sigma inverse, basically you get the formula. But the formula is of this form. And if you remember where this came from modeling the data within each class using a probabilistic model. So P of X given Cj. So the approach that logistic regression says is that, hey, look, let me just bypass this modeling because, that probabilistic modeling and, figuring out the covariance matrix and the parameters of the distribution is a little harder. Let me just say that I'm going to model the log priors, the log ratios of the probabilities with a linear function. So what logistic regression says is, suppose I have a K-class problem. Then I'm going to look at log of PC1 given X. And for all these probabilities, I will normalize them or take the ratio with respect to the last class. And I'll say that this log odds is W naught plus, let me just call it W1 tilde transpose X because I don't want to be carrying this around. And this is W1 transpose X, okay, where, X has, this is X bar, and X has, the bias term 1 in its first coordinate. And then I have log of P C2 given X, P C K given X is equal to W2 transpose X. Okay. And what we are going to do is we'll need to find the W's, right? That's what we need to find. And similarly, I can go all the way. So I have K minus 1, P C K minus 1 given X divided by CK given X is equal to WK minus 1 transpose. Okay, so this is now my first equation, second equation, and k minus first equation. Okay. And just for simplicity, because I don't want to carry this around, I'm going to do a bunch of algebraic manipulations. Let me write this, write P Ci given x as Pi. Okay. And if I do that, right, then I get that, my first equation is log P1 divided by P2 is equal to W1 transpose X, which means that P1 given divided by P2 is equal to e to the power W1 transpose X. So this is first, okay. And similarly, I'll get, oh, did I do P1 divided by P2? I should have
That's a
done.
PK.
Yes, perfect. I actually got this before you did.
Yeah.
Okay. So I just realized when I saw it that, yes, this should be PK. Okay, because we are dealing with a general K-class problem. Okay, so similarly, we'll have P2 given divided by PK is equal to e to the power W2 transpose X. And all the way till PK minus 1 divided by PK is e to the power WK minus 1 transpose X. Okay, and remember, what we want to try to find is the W's. The W's that, give us good predictions. They fit the training data, plus they are good on a new point. Okay, so let's do again some algebra. So what we are going to do is, we'll see that it's actually going to be easy to add.
Ask where did W0 went?
Oh, so remember that I did this thing where
Oh yeah.
I basically, put W0 and W1 tilde into W1.
Right.
Right? So the X is D plus 1 dimension. So each Wi
Has the
is R D plus 1. Okay, and similarly, X belongs to R D plus 1. It's just taking the first feature or first component of X is 1.
the bias. Thank you.
And it accounts for the bias, exactly. Okay. So if I now add up all these equations, 1 plus 2, and the reason I'm doing it is because if you see on the left-hand side, right over here, I have P1, P2, Pk minus 1. And remember, we are modeling these as probabilities. So the sum of all the Pi's will be 1. So if I add all these together, since they have the same denominator, I will get P1 plus P2 through Pk minus 1. And then, of course, on the right-hand side, I'll get something. But then, since the sum of the probabilities adds up to be 1, I will end up getting this to be 1 minus Pk divided by Pk. Okay, so let's do that. Okay, because that'll help us simplify things. So this implies that I'll get P1 divided by Pk plus P2 divided by Pk plus Pk minus 1 divided by Pk is equal to e to the power W1 transpose X, that's from here, plus e to the power W2 transpose X, that's from here, okay? And then I'll get e to the power WK minus 1 transpose X. And this will be P1 plus P2 plus Pk minus 1 divided by Pk is equal to summation of I equals 1 to k minus 1 e to the power Wi transpose X. Okay, but by the way, what I'm actually teaching you is like sometimes the favorite interview questions. If you interview for, machine learning position in industry many times. Okay, so if I look at the numerator, I have P1 to PK minus 1. I'm adding them, right? And okay, I see there's something in the chat. Oh, Anas, you should have asked this question before. Is there a specific set of lambda values that we should be training? Why don't we come to this later? Huh? Nilesh, can you just remind me, because I think this is about the homework. Huh? Okay, so I get, this is 1 minus pk divided by pk is equal to summation of I equals 1 through k minus 1 e to the power wi transpose x. Okay, so I can take pk to the other side. I can write it as 1 minus pk times summation I equals 1 k minus 1 e to the power wi transpose x. Sorry, I'm taking maybe more time than I should, but it's okay. Just keep me honest, make sure that I'm not making any mistakes. Okay, so this means that pk is equal to 1 divided by 1 plus okay. And what is pi? Let's see. Oh, here it is, right? Pi divided by pk is this, right? So I have pi divided by pk is e to the power wi transpose x. Okay. So since pk has this form, by the way, I don't want to confuse you with I and I. So remember, this is a summation sign, so I'll just put it as j. Okay. This means that pi is equal to E wi transpose x divided by 1 plus summation of j equals 1 through k minus 1 e to the power wj transpose x. Okay, and this is for I is equal to 1, 2 through k minus 1. And you can confirm that the sum of all the pi's will then be equal to 1. Any questions so far? Okay, so remember, I'm just kind of really done algebra right now to find out the form for pk and the form for pi, p1, p2 through k minus 1. Okay, but remember that these are the parameters w1, w2, w3, wk minus 1. They are all parameters. Okay, and then the question that we have is, how do we find them? Okay, so the parameters are usually going to be found by something called maximum likelihood estimation. Okay, so we are going to look at now the details. Okay, so the parameters in logistic regression. Okay, and these are wi. And remember, how big are these? D plus 1. And how many? I equals 1 through k. Okay. And they are going to be, and usually fit by maximum likelihood. Okay. And we'll see. So this is kind of very similar to the again the least regression case. You know, we could have actually shown that this was, if we had done probabilistic modeling, we could have shown that the least squares problem arises from maximum likelihood. Okay, so that's what we are going to use over here. Okay, so to simplify it, to derive it, let me consider the simple case of a two-class problem. Okay, so in that case, I have just y1 and y2, and I'll actually use a different encoding for y's. Okay, so let's consider a two-class problem. I need to figure out PC1 given x, right? And remember, that's what we were calling P1, but and I have P2, so I have P1 and P2, but P2 is 1 minus P1. So let me just call this as P, so I don't have to carry around this index, and P of C2 given x is 1 minus P. Okay, because obviously P of C1 given x plus P of C2 given x add up to 1. Okay, and do remember that, you know, we are modeling it. So P is so it's actually a function of W. Okay, W are my parameters. Okay, so I have training data xi, yi is training data. Okay, I assume kind of it is, you know, as before, it's kind of IID. So here is the following encoding I'm going to use this time. Okay, is that let yi equals 1 when xi belongs to C1, yi equals 0 when xi belongs to C2. Okay, instead of using kind of indicator vectors, that's what I'm doing. So I'm going to try to figure out one W, okay, that either gives 1 or 0. Okay, and what I want is that when xi belongs to class C1, I want the prediction to be close to 1. When xi belongs to C2, xi belongs to the training data and C2, then I want it to belong to the yi to be close to 0. Okay, so I can look at kind of the data likelihood. Okay, and I'm basically going to try to maximize that. Okay, and I can write that as, let me just first write it, is the product from I equal to 1 to n, p to the power yi times 1 minus p to the power 1 minus yi. Okay, so just to sort of understand what's going on, remember you have xi, yi. If xi belongs to ci, you want your corresponding yi equals 1. Okay, so what does this evaluate to? What does this evaluate to when xi belongs to ci? Right, so I have p of yi 1 minus p times 1 minus yi. So if yi equal to 1, I get this equal to P raised to the power 1 times 1 minus P raised to the power 1 minus 1. So it's P times 1 minus P to the power 0. So that's equal to P. Again, that's what you want, right? And similarly, you'll see that when yi equal to 0, then this will evaluate to 1 minus P. So the data likelihood is given by this, is taking the product, okay? But, we have exponentials, so it's better to look at log likelihood. Log likelihood, okay, because log is a monotonic function. Okay, so my log likelihood is, I'm basically taking log of this expression. And remember, this is a function of W, right? Don't forget that this prediction is going to be, or P is going to be a function of W, and that is what we need to find out. So we are going to try to maximize the log likelihood. And by doing that, we are going to be able to find the corresponding W. Okay, so if I take log of this quantity, right, I will get summation. The product turns into a summation. And I have log of P yi times 1 minus P 1 minus y. This is equal to log of P of yi plus log of 1 minus P 1 minus yi. Okay. This is fine. And then this is equal to I equals 1 to n yi log of P plus 1 minus yi log of 1 minus P. Okay, so when I was saying that this is like a favorite interview question, sometimes someone might just say, hey, go to the whiteboard and can you derive the log likelihood for logistic regression? Okay, so this is what you would do. And then, of course, how would you find the parameters, right? So you want to try to maximize the likelihood of the data or the log likelihood. Okay, so remember that this is a function of W, right? Because P is a function of W. So my log likelihood is here, and I'm going to try to maximize overall W. Okay, so maximum over W, and it is summation of I equals 1 through, and I'm just copying what's written above, yi log of P plus 1 minus yi log of 1 minus P. Okay, and this is all within the summation sign. So this is what I want to try to maximize. And remember, I have a W over here. And this is because P is a function of W. Okay, so why don't we now write it out? What we had. If you go back, okay, we had PI. Okay, so in this case, we have just P1. So P is e to the power W transpose X divided by 1 plus W transpose X. Okay, because we are only considering a two-class problem. Okay, and we've encoded it in such a way that we just want 1 W because it's a two-class problem. So P of W is e to the power W transpose Xi Okay. 1 plus e to the power w transpose xi. And 1 minus p is 1 minus e to the power w transpose xi divided by 1 plus e to the power w transpose xi, and that's equal to 1 divided by 1 plus e to the power w transpose xi. So this means that log of p, okay, if I take the logarithm of this quantity, I get w transpose xi minus log of 1 plus e to the power w transpose xi. And then if I take log of 1 minus p, that becomes minus log of 1 plus e to the power w transpose xi. Any questions? Okay. And then again, I want to maximize. Okay. And this will turn out to be like a concave function, right? So I can set the gradient equal to 0. And it's a concave function. So if I try to maximize it, I need to set the gradient to be equal to 0. Okay. Now, if you think about the gradient of this, gradient of LW, remember LW is here. So it'll basically involve gradient of W log of P and gradient of W log of 1 minus P. Okay. So this, the gradient will involve log of P and the gradient of log of 1 minus P, right? There's one log of 1 minus P. So let's first kind of look at that. So log of P is given here. And if I differentiate this with respect to W, remember I'll get just xi over here. And then this is log, so I'll get 1 divided by this quantity. And then I have xi. Okay, so it'll be of this form. Okay, so if I have this, okay, so just look at over here. And the gradient is xi minus log, I take differentiate it, I get 1 plus e to the power w transpose xi, okay, times, well, I have e to the power w transpose xi times xi. Okay, if I take the gradient of this with respect to w. Okay, and I can write this as xi times 1 minus e to the power w transpose xi divided by 1 plus e transpose. And then I also need to, if I need to take the gradient of the log likelihood, I'll need to take the gradient of log of 1 minus p, right? And so if I look at log of 1 minus p, it's given over here. It's actually a little simpler, right? It doesn't have this term, and it has the identical term over here. Okay, so it basically just becomes the second term over here, right? This term. Okay, so it becomes minus e to the power w transpose xi divided by 1 plus xi times xi. Okay, so now let's put these things together. Okay, so remember, this is the likelihood, log likelihood. Okay, so if I now look at gradient w L of w, that is equal to, well, I have the summation I equals 1 through n. I have yi gradient with respect to w of log of p plus 1 minus yi gradient with respect to w of log of 1 minus p. Okay. And then let me just copy things from above. I equals 1 through n, yi. I have this is equal to this. So I copy that, write it here, is xi times 1 minus e to the power w transpose xi divided by 1 plus and then I have the remaining term, which is plus 1 minus yi. And then I have gradient of log 1 minus p that I get from here. And so I substitute that over here. Okay. So I have this, and I substitute that over here. So it becomes minus e to the power w transpose xi divided by 1 plus e to the power w transpose xi. Okay. Let's see if we can expand it out. I equals 1 through n. Okay, well, oh, I did miss something, right? I did miss this xi. Okay, remember that there's this xi. I noted it down here. I forgot it over here. So it is xi. Okay, so let me take the xi common. So remember, xi is a vector. Okay, and the rest of the quantities are scalars. Right? So I have yi. Let me expand this out. Yi times 1 minus yi times this. One plus e to the power w transpose xi. And then when I do this, I get minus of this quantity, minus of e to the power w transpose xi. So just keep me honest, no? Very possible that I might make a mistake. And then I have this minus yi and minus here. So it gives me plus yi e to the power w transpose xi divided by 1 plus e to the power w transpose xi. Oh, but look at this term. This term is identical to this, except it's opposite in sign. So I can cancel this out. So I get that gradient of the log likelihood is somewhat simplified, and it is xi times yi minus e to the power w transpose xi 1 plus e to the power w transpose xi. Oh, and look, remember what this is? Have we seen this before? E to the power w transpose xi divided by 1 plus e to the power w transpose xi. Seems like it, right? Here, right? It's this. Oh, it's the probability of C1 given X. Okay. So you can see, right? For example, if I have xi, if xi belongs to the first class C1, then yi is going to be 1. And this is P of C1 given X. This is the prediction. If I'm close to 1, it'll match. If I'm far away from 1, right, it'll not match. So then I basically will change my W depending upon the gradient, right? And I want this to be actually 0, right? So to solve, to find W that maximizes L of W, and I'm not going to go through all the details, but you can show that L of W is a concave function. So if I set this to be equal to 0, okay, that gives the maximum likelihood solution. So what I need to do is summation of I equals 1 to n xi yi minus e to the power w transpose xi 1 plus e to the power w transpose xi equals 0. But one other thing that you should notice is, remember that xi is dimension how much? Is rd plus 1, right?
Plus 1, yeah.
And w belongs to rd plus 1. So how many equations are these? These are d plus 1 equations, right?
Yep.
And how many unknowns do I have? D plus 1. Okay, so I have basically d plus 1 parameters. And I have d plus 1 equations. Since xi belongs to rd plus 1. In linear regression, what happened? Do you remember we had also kind of xi, right? We had this, if you really looked at the linear regression case also, right, with least squares regression, you would have noticed that there was basically an xi times y minus x transpose w. There was none of this e to the power stuff. So it was basically a linear equation in w, and it actually had this form that it was xi times like in a little way, this is kind of the residual. or the difference from the actual value to the predicted value. So you're basically essentially getting a very, very similar thing over here, except computationally it is much more different, right? Over here you have this exponential or a ratio of exponentials. So the problem over here is that these are nonlinear equations. So in the least squares case, where we did not have this exponential, we could actually just formulate this as a system of linear equations by setting the gradient equal to 0. Here, it is a system of nonlinear equations. System of linear equations, we actually had a closed form solution given by the normal equations, and you could express it in the inverse in terms of the inverse of x transpose x. Okay? But here, there is no closed form solution. And this is the most common thing that happens in machine learning, right? Generally, there are no closed form solutions. Least squares linear regression is just a very special case where you can get a closed form solution. Okay, so there is no closed form solution. So how do we go about solving it? How do we solve for W? Okay, so we need to solve this. Okay, so we now really need to use some optimization methods. So one thing I also want to stress is that, yes, when we do least squares, when we do linear regression, we get a closed form solution. There exists a closed form solution, and you can use that to solve for linear regression. But even there, you could actually have used some iterative optimization methods to solve it. Here, it is a necessity. Okay, so we need to use optimization methods to solve for these parameters. Okay. And what are these optimization methods? Well, classically you have things that you might have heard about, gradient descent. We will talk about these methods more in class. Okay, or we can have gradient ascent. Okay, well, gradient descent when we are solving a minimization problem and we have a convex function, gradient ascent. For example, here we have a maximization problem, but the function is concave, right? Or you could have solved, the negative of this, right? And you would have gotten, you basically would try to be minimizing the negative of this log likelihood. And then you would look for a minimum. Okay, if you look at like optimization books, there are more sophisticated methods, second order methods, for example, Newton's method. Okay. And these are various ways to solve it, right? And for specific cases, you can actually develop specific solutions. So for logistic regression, you have, you can actually solve it using an iterative least squares solver. Okay. You can actually also use Newton's method over here and adapt it so that it is fast. One thing that happens is that in modern machine learning problems, N can be very large. Okay. So typical methods like gradient descent, what they will do is they will have some Wi or Wj, and they will basically go along the direction of the negative of the gradient and have an update rule of the form, Wj plus 1 is Wj minus some step size times the gradient of, okay, so this is gradient descent. Okay, and Newton's method is, Wj plus 1 is Wj minus eta, and then they have something called the Hessian, okay, of this inverse times this. Okay, let's forget about all these, but one common problem over here is that both of them require the gradient. And what is the gradient? To evaluate the entire gradient is actually quite expensive, right? If capital N is very large. So the drawback with gradient descent and methods like that is that they, at each step, requires order n computation. The drawback of these methods, and when I say these methods, I mean gradient descent, Newton, is that each step requires essentially the entire training data, order n computation. And you make zero progress until you do this. Okay, so this is not feasible when n is very large. Okay, so as a result, people use methods like stochastic gradient descent. Okay, and sometimes this is called SGD. And what SGD does is basically it gets an estimate of the gradient by just looking at a few points, or maybe just even one point. Classical stochastic gradient descent method is just looking at one training data, or you can start looking at a subset of the training data, like what's called a mini batch. Okay, so you do basically the computation then either just becomes order D, where D is the dimension, or B times D, where B is the batch size. Okay, and typically these are the methods that are used, and these are also the methods that now power the deep neural networks. Okay, so we will look in more detail at optimization methods, especially things like stochastic gradient descent or other methods that you might have heard of, like ADAM and so on, that in addition use some momentum and some orders of a second order method, because they do basically per coordinate scaling that can be thought of as a diagonal approximation of a Newton's method. Okay, now classically, if you solve it using either gradient descent or stochastic gradient descent, you also, as in linear regression, you may want to add regularization. Okay, so you may do 2 norm or 1 norm. Okay, so in practice, this some sort of regularization should be used. Okay, so that kind of concludes today's lecture, where we looked at logistic regression, and we said if we are just going to directly find the parameters, forget about modeling the covariance matrix, but by maximizing the data likelihood, I'm going to try and get the parameters. And we saw by doing some analysis that that leads to a system of nonlinear equations, D+1 nonlinear equations and D+1 unknowns, and then you can basically try to solve it using an optimization method. Okay, so any questions?
I have a question.
Yes, Vishal, go ahead.
So I have two questions. So firstly, will gradient descent be guaranteed to find will it be guaranteed to find the global maximum, since like you said like the log function was convex, right? So
Oh, sorry, it's not, I mean, the log function is monotonic, but in this case, you can show that the log likelihood for logistic regression is a concave function.
so when
So
we
you can take the second derivative and you can show that that has that property that the Hessian is negative definite.
so because it's concave, if we use gradient descent, like will
Yeah.
it be like guaranteed to find the maximum?
Yes. So sorry, just to keep the notation correct. If you have a concave function and you want to find its maximum, you use gradient ascent, and that'll, under certain
Right.
conditions, get you the global maximum. You could equivalently take the negative of the log likelihood, and you can then show that that function is convex, and you can try to find the minimum of that, and gradient descent will find you the minimum, global minimum.
Right. And then one more question. At the beginning, we assumed that all of the we assumed that the weights represent uh like certain terms in like a multivariate Gaussian. So when we plug those weights back into the Gaussian, like will it still, and we like find the covariance, like will those two terms be equal to each other? So like if we find like
No. So sorry. So just to make it clear, all I was showing over here is that when we had modeled each class as a Gaussian with covariance sigma, then we actually had gotten that the log odds of the probabilities were of this form, W naught plus W transpose X. This is when the covariances of the two classes are equal. All what that was saying is that that was just motivating us to model the log probabilities as a linear function.
so
Okay.
it was
And
so
then
we
logistic regression tries to find these parameters, right, through maximizing the data likelihood, and does not try to estimate the covariance of each class. So in logistic regression, there is no assumption that the class has a Gaussian distribution.
I got it.
Okay, so when you assume that the Gaussian has, if you do this modeling as a Gaussian with covariance sigma, you basically first need to estimate sigma. Once you estimate sigma, the answer is there for W and W naught. But it turns out it's actually not a very good method, because in practice, a lot of problems, you know, you don't need to model it as a Gaussian. And you're
Okay,
also
got it.
trying to estimate deep square parameters. So it's actually not a good method, this one. But logistic regression is generally one of the best methods pre-deep learning era.
Got it. So all this does is like it's just motivation. We're
Exactly.
not actually like assuming that like the log of the probabilities divided by like each other is a Gaussian, right?
Yeah,
Got it.
it's not assuming that these are Gaussians.
Right.
Yes. So by maximizing the data likelihood, we are basically doing, that's what logistic regression does. And these are called log odds.
Right. Got it. Thank you.
Okay, great.